Let's try another one. These are so much fun. All right, so we're going to pretend we're a manager of a retail store, and we want to build a 600 square foot. Oof. Just noticing here. I mean, that's fine, but that bugs me. 600 square foot rectangular enclosure on the store's parking lot. All right, so we're building more rectangles here. All right, so we're going to have this rectangular enclosure, and 3 sides are going to use redwood fencing. That costs $14 per linear foot. A 4th side is going to use cement blocks, which cost $28 per linear foot. And, well, what are we actually going to do? We're going to find the dimensions of the enclosure that will minimize the total cost of the building materials. So we're going to be building this rectangle. We're going to be fencing in all the different sides using different materials. And we want this rectangular area to enclose 600 square feet. And we want to keep the cost as low as possible, apparently. So let's go back and kind of diagram this out. Let's go through the process here. Now we don't have all the little steps listed out here. We're going to kind of go through this one just like you would. So the first step is diagram and introduce variables. So you're kind of going through the word problem, and you're looking for keywords. And so when I look at this, we're first building a rectangular enclosure. Rectangle. Drawing a rectangle. Here it comes. There's my rectangle. And I know with a rectangle, there's 2 dimensions, length and width. So whichever variables you want to use, I'm going to use X's and Y's just because. Nope. Remember, with a rectangle, opposite sides have the same length. So if this side has length Y, this side had better have length Y as well. Same thing, X and X for opposite sides here. All right, so that's our rectangle. And what we're going to do is we're going to be fencing this thing in. 3 of the sides are going to be using a redwood fencing. So let's suppose this side we're going to use redwood. This side we're going to use redwood. And this side we're going to use some redwood fencing. Look really nice. And then on the other side, that last side, we're going to be building this nice and strong. It's going to be a cement block. So that 4th side there is going to be built with cement block. All right, so for a rectangle, what are some of the usual type values we might be interested in? Well, we might be interested in the area. So what would be the area of this? It'd be X times Y. Sure. Maybe perimeter. We're going to be fencing this thing in. What would be the perimeter? Well, this is just where you add up the lengths of all the different sides. So it'd be Y plus X plus Y plus X. But that's probably not quite what we're interested in here, because there's some costs getting thrown around. So let's just flip over to the problem here. We actually want to find the dimensions of the enclosure that are going to minimize the total cost. So we're interested in how much this thing actually costs. We're going to be fencing this in. How much is it going to cost? And so let's go through and figure out the cost of building each side of this rectangle. Let's start with this left side here. This is going to be our redwood fencing. This one's going to be our redwood fencing. And this one over here is going to be redwood fencing. And then we have our cement block over here that's going to cost a little bit more. So how much just for this side? If the length is Y and redwood fencing costs $14 per linear foot, the cost for just building this one side is going to be 14 times y. Okay. Then let's do the cost for this side right here. How much would this side cost? Well, it's also redwood, so it's going to cost $14 per foot, per linear foot. And x is the dimension, so it's telling us how many feet make up this side right here. So the cost of building this side for material would be $14 per foot times x. So 14 times x. Same thing for this side here. The length is y. It costs $14 per linear foot. So 14 times y to build this side. And then finally, the cement block side is length x. And this one costs more. It costs $28 per foot. So 28 times x. So these four gadgets here, or these four little calculations, represent the cost of building each side of our rectangle. And you can see it's kind of related to perimeter, except now we have these coefficients that are sort of kind of putting some weight on. So these sides here are kind of weighted a little bit differently because one side is going to cost a little bit more. So kind of similar to perimeter, but again, not exactly perimeter here because there's these weighted coefficients to help us figure out the cost. All right, so the question is, we have our diagram, we have our variables, we have some interesting equations here. Now we're kind of getting ready to start up the problem. So let's figure out, we want to find the dimensions of this enclosure that are going to minimize the total cost. So we know for optimization problems, kind of once we have our diagram, once we've started thinking about it, we want to figure out the objective equation or function and the constraint equation. It's kind of our step one. Diagram was step 0. All right, so we want the objective and the constraint. So when we read through this, for the objective is the thing that we want to maximize or minimize. So you're kind of looking for some kind of wording indicating maximum or largest or smallest or minimum. And what we're seeing here, minimize. And what we want to do is we want to minimize the total cost. So that's really telling us that the objective is going to be the cost. That's what we want to minimize. And then our constraint, this is something else, somewhere else in our wording here that puts some restriction on our variables. And so usually it involves some constant. And if we're reading through, we're a manager, retail store, we want to build a 600 square foot rectangular enclosure. So this 600 square foot, that's kind of putting some restriction. It's restricting what our area can be. It's putting some restriction on what x and y can be. So our constraint here is going to be the area. So again, with constraint, you're looking for some restriction to your variables. So our cost in this case is what we're trying to minimize, so it's the objective. Our constraint is the area because we can't just build any old rectangular enclosure. No, we want it to be 600 square foot. So that puts some limitation on what we can do. All right, so we figured out our area formula from before. What was our area? Well, for a rectangle, area is x times y, but now we want x times y. We want the area to be equal to 600. So our area is going to be 600. So x times y is the area. We want that equal to 600. That's our constraint. What about our objective? Now that's the cost. So we kind of figured out how much it would cost to build everything. The cost is going to be 14y plus 14x plus 14y plus 28x. Let's clean that up. So what would it be? It would be 20, 32, 42x. I always like to put x's first. And then 28y plus 28y. So that's our cost. And we want to minimize this. So this is actually going to be a function. So let's call that function c for cost. So what was it? It was, oh, I forgot, 42x plus 28y. And that's our cost. So this is our objective. This is our constraint. And so once we have those two equations listed, then we work with our constraint equation and we solve this for either x or y. So, either one, take your pick. We could solve this equation for either x or y. I'm just used to solving equations generally for y, so that's kind of what I go to first, unless maybe the other one's easier. But I'm going to solve this for y. And so I get y is equal to 600 divided by x. And I have this new, or I've solved my constraint equation for one of the variables. And what I'm going to do is I'm going to take this and plug it right into my objective function. So I'm going to plug it right in here for y. And I always like to do my sorry. We'll plug it in right there. A little bit more space for work. All right, so we're going to plug y into right there. So when I do that, I'm going to get 42x plus 28 times 600 over x. And there's my cost equation. Now it's written, though, only in terms of one variable x. So that's going to be good for doing calculus, one variable. But let's simplify this down. We know we're going to be doing some derivatives. So let's multiply the constants here. It's not entirely necessary. We have division by x. Let's write that with a negative exponent. We know we're going to be doing derivatives. So if we do this, we get c is equal to 42x plus 28 times 600 is 16,800. And then instead of dividing by x, we're going to have x to the minus 1. So this is kind of, step 2 was solving the constraint equation for y generally, and then plugging in as our step 3. And once we have this nice simplified function, all in terms of one variable, now we're ready for calculus. So that's what's going to come next. And let's actually calculate the derivative. So step 4 is to go through our optimization methods. So we have our constraint, or our objective function, which we'll call our cost function. Let's use function notation, so c of x. And it was 42x plus 16,800 times x to the minus 1. And let's go through now and calculate the critical numbers. Well, let's actually get the first derivative. So we need our first derivative. So c prime is 42 plus, really minus when we do the power rule, minus 16,800 and x raised to the minus 2. And we're interested in where this thing is equal to 0 and where this thing is undefined. And so right now we see this term with a negative exponent. To kind of make this easier to work with, it might be helpful to try and write this as a single fraction. So if I were to do this, let's write this, instead of a negative exponent, let's write this back as a fraction. So 42 minus 16,800 over x squared. get a common denominator so we can combine these into one piece. So this would be 42x squared over x squared. And so we get 42x squared minus 16,800 all over x squared. And now with this written as a single fraction, now we can go ahead and worry about the critical numbers. So we want the critical numbers. And this is where the derivative is either 0 or undefined. So let's take our derivative. We're interested in where it's 0. We're also interested in where it's undefined. And the nice thing when we have it written as a single fraction like this is the only way it's 0 is if the numerator is 0. And the only way it's undefined is if the denominator is 0. So that's what we're going to do. We're going to set the numerator equal to 0. And we're going to set the denominator equal to 0. So if we set the numerator, what do we get? We get 42x squared minus 16,800 is equal to 0. And then if we solve this, what do we get? Let's add 16,800 to both sides. Divide by 42. So that'll give us x squared is equal to 16,800 divided by 42. Clean that up. I think we get 400 if we do that. So we get x squared is equal to 400. And then from there, we want to get x by itself. So we're going to apply the square root. Now, when we're solving for x, and whenever we apply the square root, it's not already there, we're applying it, plus minus goes in front. So plus or minus the square root of 400, and that's a nice perfect square. We get x is equal to plus or minus 20. Now, plus or minus 20 is possible critical numbers. But we also want to look at where the derivative is 0. So we're going to take our derivative, which is x squared. We're going to set that equal to 0. And if we solve that, that gives us a solution as well. That gives us x equal to 0. So right now, it looks like we found 3 potential critical numbers. Plus positive 20, minus 20, and 0. Now there is kind of an additional constraint going on, and that's because we're talking about building a physical thing. So kind of important to note, we're actually talking about physical dimensions here, length and width. So length and width, we're really not interested in negative lengths. So that means we want the length to be greater than 0. So that means x and y are going to be, whatever we find, we want them to be bigger than 0. And so really when we talk about this constraint or this objective function, this cost function, x can't just be anything. X has to be greater than 0. So the domain here is really the interval from 0 to infinity. So yeah, we found all these other x values that they're kind of artifacts from just the equations. But if we put them into the bigger context of the physical problem here, it doesn't really make any sense to have negative 20 as a length or 0 as a length. So the only one we're going to use here is x equal to positive 20. And that's because, again, we're only looking at the domain here. So yeah, there's other values, negative 20, 0, but they don't really mean anything in terms of this problem. We're only interested in x equal to 20. All right, so that's our only critical number on our domain from 0 to infinity. So now we found our critical number. So x equals 20 is in the domain. We don't have any division by 0 at x equals 20. Actually, if we go back, x equals 0 is undefined, so that's not in the domain anyways. But at 20, perfectly fine. 20 we can plug into this all we want. So we found only one critical number. So now we actually want to go through and we want to test that critical number. So that's the second part of this, is we want to test our critical number to figure out if we have a max or a min. And for our tests, a lot of times second derivative test is it's the quickest. So that's what we're going to do here. We're going to do our second derivative test. And so what was our first derivative? C prime is 42 minus 16,800 x raised to the minus 2. And then we're going to calculate the second derivative, which, if we differentiate this again, what do we get? We get 33,600 x raised to the minus 3. And we're going to take our second derivative, or our critical number, which was 20. We're going to plug it into that second derivative. And the numbers here are getting kind of big. But that's not a problem, because we're really not interested in the actual value here. We're just interested in whether it's positive or negative. So if we're looking at this, this is positive and this is positive. So we have a positive number times another positive number. The result is positive. And so what that means, if the second derivative is positive, that means concave up. And if we draw in our concave up shape, that's what we're looking like. So we have a local min at x equals 20. And so not only do we have a local min at x equals 20, this was the only critical number, so it's the absolute min at x equals 20. It was the only we only found one critical number on that interval from 0 to infinity. So it not only is this a local min at x equals 20, it's an absolute min. All right, so that's our second derivative test. We had our first derivative, we calculated our second derivative, we plugged our critical number into the second derivative. The numbers were kind of getting big, but we just kept track of the sign. So positive times a positive gives us positive. To help us remember what the second derivative test says, just think of that in terms of concavity. So this is concave up. Draw our concave up shape. And when you draw that, it looks like a min. And that's what we actually have, is a min. So we have a local min at x equals 20. And because our domain here was just the positive numbers from 0 to infinity, and we only had one critical number on that interval, so remember back, we had some other possible critical numbers, negative 20 and 0, but those were really not important for our problem because we're talking about physical lengths. So we're actually kind of narrowing our attention to just the domain of being from 0 to infinity. And so we know we're going to have an absolute min. We're just about done. And the last thing we want to do is we want to make sure we answer the question. So what are we? This is kind of step 5. Make sure we answer the question. It's easy to kind of forget what we're actually interested in. And that is, we want to find the dimensions. And we want to use units where applicable. So we found one of the dimensions, x equals 20. And our units here for length are feet. And then we want to go and find, well, what is the dimension of what is y? And so this is where we use our constraint. So we found previously from our constraint equation, when we actually solved this, let's go back, where was that? right over here. We figured out what y was in terms of x. So let's use this. Well, we'll do it right here. Y is 600 divided by 20. And if we do that, what do we get? 30. So, come back to your constraint equation where you actually, you could go back to this one, but we've already done some of the solving here. So go to this one. It's a little bit quicker. And we see that y is 30. So cost is minimized when x is 20 and y is 30. And the units there are feet. And so just make sure you go back to your constraint equation to find y. So you just want to make sure you're actually answering the questions. The problem here is find the dimensions. If the problem said find the total cost, well then you would take these x and y values and you would plug them into your cost function to figure out what the total cost would be. But in this case, we're just trying to find the dimensions. So get x, get y, and make sure you're using units. All right, good one. That's a good one. So you kind of get a little bit more. There's a little bit more here in going on with our derivatives and doing our tests. So this is a good one to practice. All right, probably one more. We'll do one more example. These are too much fun. So we'll do another one. We'll see you there.